Slide 1. Plate Tectonics, Topic 11A, Part 1, The Observations. Slide 2. Plate Tectonics. Plate tectonics is the name given to our modern theory of how the Earth works. It helps us understand how and why earthquakes, volcanoes, mountains, trenches, islands, oil deposits, and much more occur when and where they do. The basic idea of plate tectonics is that the Earth is covered by a cool, thin, solid outer layer called the lithosphere, which floats on a warmer, denser layer which can slowly flow, called the mantle. I like to describe the mantle as semi-solid. It is not solid because it flows and changes shape, but it does not flow as easily as a liquid. Toothpaste is an example of a semi-solid. Beneath the mantle there is one more layer, the superhot Earth's core, which is at the center of the Earth. The lithosphere is broken into pieces called plates. The semi-solid rock down in the mantle moves due to heat it gets from the Earth's core. The motion of the mantle pushes the plates away from one another in some places, like the mid-ocean ridge, and into one another in other places, like trenches. Plates separating and colliding causes earthquakes, volcanoes, mountains, trenches, and so on. Slide 3. The lithosphere and the crust. The lithosphere is made up of two parts, an upper part and a lower part. The upper part of the lithosphere is called the crust. The lower part is made of solidified mantle rock. There are two kinds of crust. Continental crust is made of lower density, lighter colored granite. Oceanic crust is made of higher density, darker colored basalt. Thus, continental lithosphere has granite on top and solidified mantle rock on the bottom. Oceanic lithosphere has basalt on top and solidified mantle rock on the bottom. Bedrock is the solid rock beneath the sediments that cover most of the land and ocean floor. The bedrock of the continents is made of granite, and the bedrock of the ocean floor is made of basalt. Since granite has a lower density than basalt, continental lithosphere has a lower density than oceanic lithosphere. Notice in the diagram above that a plate can have continental crust next to oceanic crust. In other words, one plate can consist of some continental lithosphere and some oceanic lithosphere joined together, side by side. Slide 4. The observations support the theory of plate tectonics. A vast amount of observational evidence from both the continents and the ocean floor supports the idea that the continents move, continental drift, the ocean floor moves, and that oceans grow and shrink. There are three main ideas that a growing body of evidence began to support and that led to the development and adoption of the theory of plate tectonics: continental drift, sea floor spreading at the mid-ocean ridge, and subduction at trenches. Continental drift is the idea that the continents move. Sea floor spreading is the idea that the ocean floor moves away from the mid-ocean ridge, splitting the ridge apart. Lava from inside the Earth comes up into the resulting rift, gap, hole, in the ocean floor to fill in the rift. When the lava comes into contact with cold ocean water, the lava cools and hardens into solid rock and becomes new ocean floor, new lithosphere. Subduction is the idea that the ocean floor bends and goes downward into the Earth at trenches in the ocean. As the ocean floor goes down into the Earth, it warms up and melts back into the mantle. Thus, the ocean floor is destroyed at trenches, lithosphere is destroyed at trenches. Evidence: the matching of the edges of the continents and of features along the edges of the continents. If you examine the coasts of South America and Africa, you can see that they match rather nicely together. The match is even better between the edges of their continental shelves. The east coast of North America and northern Africa also match, as do other parts of the world. Not only do the shapes of the shorelines and continental shelves match, but fossils, mineral deposits, like coal and diamonds, mountain ranges, and more, match along the edges of the continents as well. The matching of these features suggests that the continents were once connected to one another and therefore they must have moved to reach their current positions. If the continents were not connected in the past, there would be no reason for the features to match. It would simply be a coincidence. In principle, it is possible that all these things could match by random chance. After all, unlikely things do happen. Someone wins the lottery. But when determining what we believe, we typically favor ideas that are more probable, not less likely. In other words, arguing that these features of the continents match by chance would be something like saying that if you choose 7 pieces out of a jigsaw puzzle box, they are likely to fit together and produce a nice picture. This is possible, but certainly not something that most of us would expect to happen. Slide 5. The situation we are in is something like this. Imagine finding 2 pieces of paper with words on them and rough edges. When you place the pieces of paper together and they fit nicely to form one piece of paper, what would you conclude? You would probably guess they were once part of the same piece of paper. You might guess that someone used scissors to cut them apart. Could their edges match and fit together by chance? That is possible. But you also look at the words. In the places where the pieces of paper fit together, you can see that the words on either side join together to form sentences that make sense. You can read a complete story on the pieces of paper now that the pieces of paper are back together. This is like what scientists see when they examine observations from the continents. The edges of the pieces of paper are like the edges of the continents and continental shelves that fit together. The words are the fossils, mineral deposits, mountain ranges, and more that match along the edges of the continents. If both edges of the pieces of paper fit together and the words make sense together as well, it is difficult to imagine how the pieces of paper could not have been one page before. Otherwise, the same pages from 2 copies of the same book would, by chance, have had to be cut in the same shape and the matching halves discarded in the same location. To me, that seems extraordinarily unlikely. It is much simpler and more likely that the 2 pieces of paper were once joined together as a single sheet of paper. In short, it may seem difficult to imagine how or why a continent would move. However, it is also difficult to imagine that the matching of the shorelines, minerals, and fossils would happen by chance. It seems like one of these 2 amazing things must be true if we are to explain what we observe, the evidence. Slide 6. The fossil evidence and evidence for climate conditions on continents in the past. The fossils in particular are interesting. Currently, the plants and animals on different continents are different from one another. They have evolved to adapt to the present environment, things like climate, soil, vegetation, predators, prey, bacteria and viruses that cause illnesses and disease. However, land animal and plant fossils are the same on some continents, like South America and Africa, until a particular point in time, when they begin to start showing evolution in different directions. This suggests that their environment began to change and that they were no longer able to interbreed, presumably due to the separation of the continents. We also find the remains of tropical plants and tropical animals like coral reefs near the poles, and signs of erosion by glaciers, huge sheets of ice, in the tropics during the same time periods. Fossils of tropical animals at the poles can be explained if the continent they are on was once near the equator and moved to the poles. Slide 7. Evidence from the ocean floor. Observations from the ocean floor are crucial to understanding how and why the continents move. As we discussed earlier, most ocean trenches lie close to land, either continents or islands. In addition, earthquakes and volcanoes occur near trenches. If the trench occurs next to a continent, the continent has volcanic mountains near the coast, like Mount St. Helens in Washington, Mount Fuji in Japan, the Andes in South America, Popocatépetl near Mexico City, Krakatoa near the Indonesian islands of Java and Sumatra, and so on. If a trench occurs next to an island chain, then the islands are giant volcanoes, like the Mariana Islands next to the Mariana Trench and the Aleutian Islands in Alaska. The mid-ocean ridge is also a site of volcanic activity and earthquakes. Several very different lines of evidence, kinds of sediments, sediment thickness, radiometric dating, and seafloor magnetism, all suggest that the ocean floor is very young close to the mid-ocean ridge and gets older and older the farther the ocean floor is from the mid-ocean ridge. The age of the ocean floor is evidence that supports the idea of seafloor spreading, the idea that the ocean floor is moving away from the mid-ocean ridge on both sides of the ridge. New ocean floor is created from solidifying lava at the ridge. The ocean floor ages as it moves slowly away from the ridge. The farther it is from the ridge, the older it is. Note, a young rock is made of material that recently became solid rock. In the case of the volcanic rocks of the sea floor is young if it cooled from lava into solid rock recently. Of course, when geologists use the word recently, they could be discussing the last few millions of years. Slide 8. For example, the layer of sediments on top of the mid-ocean ridge is thinner than the layer of sediments on the abyssal plains on either side of the mid-ocean ridge. This makes sense if new ocean floor is being created at the mid-ocean ridge, because new ocean floor will not have had time for many sediments to fall on top of it. Ocean floor accumulates more and more sediments as it moves farther and farther away from the mid-ocean ridge over time. In addition, on abyssal plains a thick layer of calcareous ooze can be found beneath a layer of red clay on the ocean floor in some places. Calcareous ooze accumulates in shallower water, so it should not be found deep on the abyssal plains, but it can accumulate at the mid-ocean ridge and then move to the abyssal plains as the ocean floor that the sediments rest on moves away from the mid-ocean ridge over time. Slide 9. Evidence from rock magnetism. Evidence from rock magnetism provided some of the crucial evidence that made the majority of scientists switch from earlier theories about the Earth to the modern theory of plate tectonics in the 1960s. When lava cools into solid rock, magnetite particles, little iron-rich minerals in the lava, orient themselves with the Earth's magnetic field. They behave like little compass needles. Thus, the rock records information about the direction and strength of the Earth's magnetic field at the time when the lava cooled and hardened into solid rock. Scientists studied lava flows from different time periods and found that they pointed towards different locations in the past. This suggested to scientists that the Earth's magnetic north pole changes location with time. Scientists monitor the magnetic North Pole today. It shifts a couple hundred feet each year. When looking at lava flows from millions of years ago, scientists found something stunning: the magnetism in some rocks points towards places closer to the South Pole. In other words, sometimes the magnetic North Pole flips from north to south, or vice versa. This happens every 500,000 years to a couple million years or so. In fact, the Earth's magnetic field has been weakening for the last few centuries and we are due for a flip. We may actually experience a flip in the Earth's magnetic field over the next few centuries. The Earth's magnetic field helps protect us from the charged particles, radiation, of the solar wind from the sun, which not only affects background radiation, but disrupts electromagnetic networks, like radio, cell phones, and electric power grids, so this could cause some surmountable but expensive problems for future generations. Scientists found that they could not triangulate the location of the Earth's magnetic North Pole when using ancient lava flows, unlike more recent ones. However, they found that if the continents moved in a particular pattern, then the problem went away. The magnetism of the rocks from ancient eruptions on different continents all point towards the same location for the Earth's magnetic field if the continents move, and move in a pattern consistent that derived from fossils and other lines of evidence. Observations of rock magnetism from the ocean floor were the straw that broke the camel's back. In other words, observations of rock magnetism from the ocean floor led scientists to come to a consensus that the theory of plate tectonics is the best explanation for how the Earth works. The rocks of the ocean floor are magnetized pointing north and south in long stripes that run parallel to the mid-ocean ridge and are mirror images of one another across the ridge. In other words, if two stripes are on opposite sides of the ridge but are the same distance from the ridge, then their magnetism points in the same direction and they have about the same width. This suggests that rocks on either side of the ridge formed at the same time, because they were influenced by the same magnetic field, and then moved outward from the ridge together at the same speed. In addition, the thickness of the stripes on the ocean floor is proportional to the time between the flips of the Earth's magnetic field determined from volcanoes on land. In other words, the more time that passed between flips, the wider the stripe is, just what you would expect if rock is slowly moving away from the mid-ocean ridge and more rock is being added to a stripe at the mid-ocean ridge over time. A wider strip contains more rock, and a longer time period is needed to add more rock. It is hard to think of another logical explanation. Slide 10. The basics of the theory of plate tectonics. The theory of plate tectonics provides the following explanation for the observations discussed previously. At the mid-ocean ridges, the plates are separating, pulled apart by the motion of convection cells of semi-solid mantle rock beneath the plates. Lava then comes up to fill in the resulting gap and cools into solid rock when it comes into contact with cold ocean water, becoming new, young ocean floor. The ocean floor cools more as it ages, making it contract, and more sediments pile on top of it, making it heavier. Thus, the ocean floor becomes more and more dense with time. As the ocean floor moves away from the mid-ocean ridge, seafloor spreading, it either pushes a continent, making the continent move, continental drift, or runs into another plate, leading to earthquakes. When two plates collide, both plates cannot occupy the same location at the Earth's surface, so the plate with the higher density dives into the interior of the Earth, making the seafloor deeper, creating a trench. We say that a plate diving into the Earth subducts. The diving plate begins to melt in the hot mantle, creating some hot, low-density magma which works its way back towards the surface through the plate that does not subduct, creating volcanoes. Over time, more and more lava comes out of these volcanoes, and cools and hardens, building tall piles of rock, mountains on continents or islands and seamounts on the ocean floor.